Hello, this is Purnima Gautam, and our team is going to present on the topic wind farm layout optimization and application of AI in energy transition. So, this is the joint work done by Anwesha, Atif, Debjyoti, Laveena, and myself. Coming to the next slide. The timeline of our presentation includes introduction, literature survey, proposed solution, improvements, conclusion, and future scope. Next slide. Introduction. With the growing population and rising demands leading to climate change, the planet is in need of a cleaner and a smarter energy solution. The energy sector needs to transform itself from fossil waste solution to a zero carbon emission system. So, this can be achieved by adopting renewable source of energy. As we can say that India has over 35 gigawatt of installed capacity from wind power, representing nearly 47% of the total energy output from the renewable sources. So we can say that the wind energy is the fastest growing source of renewable energy. Coming to the next slide. So there is one question: why wind farm layout optimization is needed? Wind farm layout optimization is to find the optimal positions of wind turbines inside a wind farm. The key problem with an unoptimized layout is the combined influence of arranged wind turbine on the wind speed distribution across the limited area of the farm. So a wind turbine extracts energy from the incoming wind. It creates a reason behind it downstream where the wind velocity is decreased. That is called a wake reason. Due to the induced speed deficit, a wind turbine placed inside the wake reason of an upstream turbine will naturally generate reduced electrical power. So the inter-turbine interface is known as the wake effect, and this wake effect reduces the power production. So while we do the wind farm layout optimization, our aim is to minimize the wake effect, and therefore the expected power production will be maximized. Coming to the next slide. So we are working on this problem in this presentation. We worked upon problem statement given by the Cell AI hackathon. It focused on sustainable and affordable energy requirement for optimization of wind farm layout. We were given a hypothetical 4 cross 4 kilometer, a 2D offshore wind farm, in which our objective was to optimize placement of 50 wind turbines of 100-meter rotor diameter and 100-meter height. So we were given the orientation of the farm, which was aligned with the geographical east and north direction as x and y axis. We were given some of the constraints like the perimeter constraints and proximity constraint. In the perimeter constraint, minimum clearance range was decided as 50 meters from the farm boundary, and the proximity constraint, the distance between two turbines must be at least 400 meters. And also we were provided with some of the CSV file which were having some of the contents regarding the problem. So now Laveena will be taking over the literature survey. Thank you.
In the literature study, we'll be discussing about some work which is related to wind farm optimization and how it is relevant to our work, and how are we improving our work given the work that has already been done. A wind turbine basically transforms the mechanical energy into electrical energy, which is further used to do tasks like pumping water, mill grains, etc. And the efficiency in extracting best outcome from wind farms lies in many multiple factors, some of which are stated below. What is like shape of the wind turbine, location of the farm, and farm layout design, etc., etc. Hence, optimization of power output from the wind farm is a multi-dimensional problem with high complexity. So AI plays a very important role in finding a solution for this heterogeneous problem. So one of it is heterogeneous One of the literature studies that we included in our work was heterogeneous machine learning assemblers for wind power prediction in use like that used various features and gave us a profile of the optimal features which are very crucial while uh, designing this algorithm. So, and this paper also highlighted that wind farm optimization is one of the most crucial feature. As we know, an unoptimized wind farm layout leads to a lower wind power capture and than expected, and it leads to higher maintenance costs. Uh, in the next slide, we are discussing about two major layout optimization approaches. One is grid-based, which is mostly exploited because it is easy to obtain a local minima in a subdomain rather than in a bigger space. So the farms are divided into cells of equal size and turbines are kept in the center. And an unrestricted layout where turbines are placed in any position within the farm. And in the next slide, I'll be talking about some related work that we have seen and kind of tried to analyze how this works out. So in the first work, the researcher has divided the farm into the cells uh, of equal size, and turbines are kept in a center and unrestricted layout format where turbines are placed in any position within the farm. And he used a genetic algorithm which resulted in maximizing the power and decreasing the cost. The researcher also used a grid-based approach, and he got an optimal placement of turbine within the farm using a discrete representation of farms, and hence increased the expected power generation. And the third one is really interesting because it used an unrestricted layout approach, which solved a very complex nonlinear optimization problem, the wind farm model effect. And it effectively solved it effectively actually solved the constraint problem using constraint particle swarm optimization, which addresses very critical aspect of optimal wind farm planning. There are many such algorithms. Few of them are like a Monte Carlo simulation, which we are aware that it's a model that it is used to model the probability of different outcomes of a process that cannot be easily predicted due to the intervention of random variables, uh, which is actually also used by some researchers in optimizing the layout of the wind farm. And similarly, there's a algorithm which is called biography-based optimization algorithm that has actually been able to outperform various other conventional algorithms which I have discussed in the first three part of the related work. It has actually been capable of outperforming all the first three ones. Thank you. And now Atif will be talking more about methodology in our work.
Hi everyone. So this part we'll be talking about the methodology about our work. So before we started off working on the actual algorithm, we decided to take a diversion and try to simplify the problem, work on that. So by simplification, what we really mean is that we know the perimeter constraints that they provide to us was that we cannot, the turbines have to be placed from 50 meters away from the edges. That means 50 meters on the left and 3,950 meters on the right on a 4 by 4 kilometer grid. So if you want to discretize this problem, why do we want to discretize? It's because of the proximity constraints that two turbines need to be at 400 meter apart. So in that case, what we can do is we can just subtract 3,950 minus 50. So that gives us 3,900 meters, which is the total distance or area that we have. And 3,900 meters divided by 400 actually gives us approximately 9 boxes. So 9 by 9 boxes, that means 81 boxes. So now the problem has boiled down into placing 50 turbines on 81 boxes. So there are multiple ways of doing this. One of the more prevalent methods is genetic algorithms, and as we have seen in literature. So before actually going to the genetic algorithm phase, We did not supply the GA by simple random initialization. What we did was rather run. We placed 50 turbines and 81 boxes in randomly for over like 100 or 1,000 iterations. And as you can see, this visualization that multiple different configurations are produced, and the configuration that gave the maximum AP was chosen as the start state for a genetic algorithm. So the genetic algorithm ran, and it used whatever, like it ran for its life cycle and the usual methods that are involved in the genetic algorithm. And finally, it gave us a solution which looked something like this. And this solution gave us an AP score of about 532 based on the public leaderboard that was actually provided to us by the Shell hackathon. That's actually present on the website. We looked up our solution and found that our solution gave us a score of a rank of 150, 159. So obviously this was a good start, but we can definitely do better. So what can we do next? So before we actually dive into the main issue problem, what we did was we went back to the drawing board and we decided how things are done in wind farm layouts, and we realized that uh, one of the best methods to actually get the most optimal solution is to place maximum turbines on the edges. So what we did was we took turbines and we placed them around the edges, which gave us 10 plus 8 plus 10 plus 8. It means the top, left, bottom, and right edges. So that gave us a total of 36 turbines, and the remaining 14 turbines were randomly placed. Now, next, how do we optimize these 14 turbines? So, if you think about it, really, it's very related to the n queens problem. So, in our classes, we are taught about the n queens problem, wherein we have to place n queens on an n by n chessboard, and in such a way that none of the queens attack each other. So, in a similar way, we have to place 50 turbines in 81 boxes. So, but there are two dissimilarities here. Firstly, placing a turbine, finding in the optimal placement such that all the turbines are actually 400 meter apart does not guarantee us that we get an optimal solution. But for NQs, obviously, if we get one placement, correct placement, that's the optimal solution. Secondly, the biggest problem that we face is that N-Queen's problem is basically solved by using backtrack, which is a part of the dynamic programming scheme. And in our solution, if you think about it, if you actually really think about it, discretizing the problem uh, causes a large search space to simply be removed. Why is that? Because we are not because even the slightest amount of change in position of a turbine actually gives us a new state. That means a new part in the search space. So by considering only a discrete version, we are simply throwing away a huge portion of that search space, and that is not what we want. So you want to go for a continuous space, and in a continuous space, if as I said, if you move even a little bit, it gives us a new state. So for all practical purposes, this entire search space is infinite. So in that case, a dynamic algorithm will completely and miserably fail. Therefore, we require a greedy algorithm. So now we know that whatever algorithm we design, it has to be greedy. So coming to the actual algorithm, so it's a very basic algorithm. What we did was since it is going to be greedy algorithm, we require some sort of heuristic to traverse the search space. As I said, since it is a greedy algorithm, what we can do is we can see each turbine individually. So we pick up a single turbine and we find out its possible directions of movement. Here we assume that since it's a 2D space, we can move in 8 possible directions. That is the usual north, west, south, east, and so on. So in each direction, we move the turbine by some amount, which we call the learning rate, and we find its score. So based on this setup, we get about 8 scores, and then we move the turbine in that direction, which gives the maximum AP score. So this is the basic algorithm. This is heavily inspired from a neural network learning strategy, wherein what the neural network does is basically it tries to find out the error and then it backpropagates. By backpropagation, what do we mean is that we simply find the direction of the best possible movement and then we move there by some amount. In a similar fashion here as well, we are moving in a similar amount, but there is no requirement for any differentiation. That is, we have a non-differential optimism. So this was the concept of our algorithm, but obviously this is really simple and we made multiple improvements upon this, which will be further explained by Anwesha.
This is Anwesha and I'll be discussing about the improvements that are being made on this algorithm. Next slide. So here we have fixing proximity constraint. As it is understandable, moving a turbine individually may violate the proximity constraint with other turbines. Now, till this position, the states which were actually producing this kind of violations were discarded. But these states may actually contribute to a better score if the violations are fixed. Also, it has already been mentioned before that NDOPD is a non-differentiable cost function and uses a non-differentiable cost function, and hence it can be re-implemented to output the minimum distance of the current turbine with all other turbine as its cost function. Now, the best direction to move in this case is the direction which leads to an increase in the minimum distance until all the turbines are at least 400 meters apart. This results in an algorithm that can fix any constraint violating layout. Let's assume that the turbines are identified as T1, T2 to T50. For a turbine Ti, its distance with the rest 49 turbines are calculated and the minimum distance is given as an output by the cost function. Let's say turbine Tj is having the minimum distance d with turbine Ti. In that case, the goal is to move the turbine Ti in the direction such that d is at least 400 meters. Now, all of these consequence improvements and additions are applied to NDOPT also subsequently. Next slide, please. Shuffling. Now, NDOPT updates the position of each turbine individually at each iteration. It is clear that the turbines updated before others receive higher priority, with the first turbine practically deciding the course of traversal through the search space. This is because once a turbine's position is updated, the next turbine's local optima is calculated with respect to that of the previous one. This causes the algorithm to traverse only a subset of the search space, which is definitely not ideal. Therefore, after each iteration, the turbines are shuffled so that the sequence of updation changes. Next slide, please. Now, this is pretty straightforward. Once the direction for the best position is found, instead of moving the turbine by a constant learning rate in this direction, multiple different learning rates are tried out and the one which gives the maximum AEP is selected. So let's say we have n discrete distinct learning rates R1, R2 to Rn. To find the direction for moving turbine Ti to its best position, the learning rate with the minimum value is selected. After finding the direction, each and every learning rate R1, R2 to Rn are tried and the one giving the maximum AEP is selected. The feature drastically improves the convergence and also therefore each turbine at any given epoch moves by a different learning rate. The next portion of the improvement is going to be taken care of by Debjyoti.
Hello everyone. Apart from the above mentioned improvements, one of the other improvement that we did in our algorithm was the increased degree of freedom. So as described by my colleague earlier, that in order to change the position of the turbines, we moved it in 8 directions. So instead of moving it in 8 directions, we decided to move it in all the 360 directions. But further, we realized that by changing it just 1 or 2 degrees, there wasn't much change in the AEP score. As a result, we settled at 36 directions, with each directions accounting for 10 degrees. As a result, the location of the turbines was indicated by cos theta, where the x was denoted by cos theta and y was denoted by sin theta. So this was one of the other improvement that we did. Further, moving on, as we know that our algorithm, this algorithm non-differentiable optimizer is just another optimization problem. So one of the key vulnerability of optimization problem is to get stuck in the local optima, and NDOPT being no exception also is susceptible to this kind of problem. So in order to get over with this problem, what we did was we added some noise whenever the search space or the search space would fall into any local optima. Uh, and after and every time the algorithm or the learning rate will get stuck in the local in such kind of local optima, there would be a counter variable which would be increased exponentially and hence scaling the noise as well. So this would not only help the search space to this will not only help the algorithm to get over the local optima, but it will also help to explore the entire search space. So further, so apart from all these improvements, what we also did one of the very famous ensembling technique for this, which is not much used in traditional NDOPT. So basically, the result in our solution is generated by two versions of algorithm. The first one updates the location based on the position of all the turbines, whereas the second version generates the position by only tweaking only updating the interior turbine, the location of the interior turbine. So what we did was for each and every turbine T, we would check which version of non-differential optimizer is giving the best solution, and whichever is giving the best solution, we would consider that only for that specific turbine. So this is how we would generate, or we would get the best of both the algorithms, hence giving it an essence of ensembling technique. So with this, I finished the improvements and the ensembling technique that we did in our algorithm. Now I would request Purnima to finally conclude our presentation.
Thanks, Debjyoti. Coming to the conclusion and future scope. So we can see the graph which has been made by submission versus APS score. So in the graph above, one represents our progress using genetic algorithm, and the second represents the progress made by implementing NDOPT algorithm, while the third represents the final phase that we did using the new ensemble techniques. So finding the better layout leads to the higher energy production and profit as well. So we got the highest AEP score as nearly 547. So coming to the next slide. So in the future scope, we can say that these scores are good, but we would like to improve the optimization technique using different approaches like the reinforcement learning. So here is the layout for the reinforcement algorithm, which can be used in this type of problem. The goal is to find the best operational settings of the wind turbine, depending on the wind conditions. The states is defined by the combination of wind direction, wind speed, and turbulence intensity, while the reward which the agent gets is the gain or loss in the power with respect to the nominal operations. Thus, for the future scope, reinforcement learning seems to be a good direction to move forward for getting the better results. So coming to the next slide, these are some of the references. So we can say that in this. Okay, thank you.